Okay. Sorry.
Okay.
Yeah, could be it's been really warm. Yeah, could be. Not bad, how's yours?
How'd it go, Lewin?
How'd your first couple advising sessions go?
Oh, great. That was,
You got some good students?
yeah, they were really energetic and like it suddenly breathes more. They
Professor
were all
Renew.
excited.
Professor Renew.
How are you?
Very well, thank you. How are you?
I'm fine.
Very well.
Thank you for coming.
I had to call.
It's my
I had to
pleasure.
call down to Jackie. Or no, not Jackie. Is it Melissa? No, Stephanie. Stephanie. Yeah, I had to call Stephanie one or two times.
Oh, thank you. I've been doing a lot of those myself. Leading up to this, yes.
But I was working.
Wait, for how long to train?
Yeah, she brought it in. She was a student. The scholarship that requires register for a seminar, but there was opening, so they had to open another one.
Karen, did you get some snacks?
Huh? You look too serious.
Just get some snacks. If you want some. Not healthy though.
Yeah, remember in 2 weeks I'm going to be completely immobile, so I have
Yeah,
to
I don't want to pack on any
adjust
extra
my
weight.
diet now.
Why? They didn't trust.
They wanted to see how each department handled
New
new
advice.
advising. They're trying to train their person.
Okay.
And Mary was like, I don't have any advising, but I'm going to help you. So sitting here.
Okay, so it's Mary and
It
this
was
person.
Mary and them, the two people from the
Something,
college.
no matter what I
the
say,
outgoing and the incoming from the college.
Other than you might.
Yeah.
Well, it'll be forever on the video.
Oh, that's true.
And then-
But you can focus on, you know, everything else in your mind.
Yeah.
Probably not even part of a social science experiment or something.
They did ask him to make sure it was okay. Figure stuff out. Still, a little.
There he is.
Back here by the snacks.
It's a good turnout. Yeah.
It's not planned.
Yeah, and all this pressure. Pressure makes diamonds. Yep. A lot of heat.
I don't know, do you need heat or do you just need pressure?
I don't remember.
I've heard that this industrial process for making diamonds is about to
Only
take
doing
off.
some crutches.
Oh, really?
In like 30 years, we're not going to be mining diamonds. Right.
Wasn't it more cost more to make a diamond, right?
Right now. But in the next 10 to 15 years, that'll put more geologists out of a job.
The beers will be really upset, I think, huh?
Yeah.
Well, good afternoon. I'd like to welcome everyone to Ethan Dahlhauser's final seminar and at least the beginning part of the defense. It's my distinct privilege to introduce Ethan. He's a native of Whittemore, Iowa, which is right near Cylinder. So that's right on the Palo Alto and Kossuth County line. So northwest of here, what, 120 miles or so?
Yeah, almost exactly. Yeah. Not in a straight line.
But Ethan came to ISU in fall of 2008. As you can tell, I had to look this up, make sure I had the numbers right, where he earned a double major in geology and environmental science. He graduated spring 2012 summa cum laude. That's nice. So Ethan's really fun in that he's the only summa cum laude guy I know who also has a CDL. So that's a really wonderful set of skills. So it's outstanding. While he was an undergraduate, he did field camp, which is a wonderful experience, and he also worked at the Lamont Observatory with Columbia University, where he did a project. So really wonderful background. In the summer of 13, so 2 years ago exactly, he started an MS in soil science here. And over those 2 years, he's done the project we're going to hear about today, as well as stay busy with helping TA courses for Dr. Manu, for me, a variety of other things. He also got married to April, and more recently he became a dad. So he's been busy. But
Yep.
we're not going to learn about all that. We're just going to learn
Yep.
about this. So, floor is yours.
All right, thank you, Dr. Burris, for that excellent introduction. Yeah, I'm very excited to be a father. He's not here today. He'd be a little bit of a distraction, I'm afraid. So, good afternoon. I am excited to present to you some of my research. The title of my seminar today is Pedogenesis of outwash derived soils on terraces of the Des Moines River. I'd first like to begin to acknowledge all those people that helped me along the way. Firstly, my committee members, Dr. Lee Burris, Dr. Frana Kosick, and Dr. Andrew Manu. Of course, thanking the Department of Agronomy for my assistantship that allowed me to be here, and numerous colleagues and contacts. Jenny Richter is here. She helped me a lot. Tom Lawler couldn't be here. Aaron, big help. And some geology faculty as well. And of course, most importantly, my adoring wife, April, who put up with all my graduate school shenanigans. Walking you through what I will discuss today, we'll start off with the rationale, research objectives, move on to a little bit of an introduction, discuss the methods. I'll present my results, and we'll conclude, and then have some question-answer discussion time. Rationale for this project. Outwash derived soils, the soils formed in glacial outwash, constitute around 3% approximately of the state of Iowa. Put that in perspective, that might be about like 3 counties in size, but of course spread across the state. We observe on NRCS official series descriptions that these soils often have loamy soil textures overlying coarser, sandy soil textures. The depths to effervescence also have been observed to increase as we move across the state of Iowa from northwest to southeast. So does the leaching of carbonates significantly influence the morphology and physical properties? The objectives. We'd like to, of course, since this is a pedology study, find out profile origins. Specifically, we'd like to understand that textural difference, that break, the finer loamy textures over the coarse textures. And is this geogenic, so from geology, or pedogenic, changes later on? We'd also like to, we tried to estimate the mass of carbonate minerals that have been removed from the upper profile at these study locations, and determine trend across Iowa for the removal and leaching of carbonates across the state. The hypothesis. Basically, the null hypothesis is that the soil profiles that we observe are mainly a result of the inherent properties of the parent material, the outwash. The alternative hypothesis would be that these profile characteristics are a product of pedogenesis, or soil formation. So, lines of evidence that you would maybe look for to support your null hypothesis. One would be, can the textural variation be explained by waning flow during outwash deposition, say following a higher energy flow? So, so outwash, of course, is being deposited by glacial meltwater. A drastic increase, so I was saying loamy textures over coarse textures. We see a drastic increase in gravels, pebbles, and coarse sand below the surface horizons. Bedding planes would be strong evidence as well. To support the alternative hypothesis, perhaps absence of carbonates and any well-developed horizons, such as seeing an argillic horizon. Pseudomorphs, that is to say rock coarse fragments that have broken down into like their mineral grains or constituents, but you can still see those pockets of where that rock, that stone once was, and also any concentration of a stone line within the profile. Moving on to an introduction. So we have people here of some diverse backgrounds. So I'll start off with what is outwash. Simply, it's sediment deposited basically by glacial meltwater in front of a glacier. It normally consists of sub-rounded to rounded sands and gravels, representing bed load, and usually very little silt and clay. Now it depends on how close you are to the meltwater source, to the glacial source. This is a useful block diagram just of some common glacial landforms. You can of course see the glacier, and laser pointers don't work on the screen, so I'm going low tech. You have this glacier here, of course, and this is your glacial stream. You can actually think of this as perhaps the Des Moines River. At the time of its birth, so to speak, it would have been emerging from the glacier itself and depositing outwash in the outwash train. These are some other common glacial landforms that aren't necessarily relevant right now, but you can see the end moraine and such. This is a map of the major landform regions of Iowa. Many of us in this room are familiar with this and have seen this many times. I'd like to point out in black is the Des Moines River, this river here. You can see the other drainages in Iowa, the other streams and rivers, major ones. You of course have the West Fork and the East Fork, and where they join together is about Humboldt. Now, the outwash studied in this project is all Wisconsin age outwash. The Wisconsin age outwash was deposited in along streams that their headwaters are from the Des Moines Lobe, because that's the most recent glacial deposits in Iowa of late Wisconsin age. These major landform regions are basically controlled by our recent, well, geologically recent past and what's been going on in the past few 100,000 years, maybe the last couple million years, mostly. I just want to flash this map briefly. This is just an old map of the Principal Soil Associations of Iowa. You can see the similarities. This is just to demonstrate that the soils in this state are largely influenced by what was going on with our geology. So you can see the similarity. This is a map of the state of Iowa, a relief map, so you can see kind of the drainage networks, the hills, the valleys, etc. I've labeled here the major moraines, the Algona, the Altamont, and the Bemis that make up, the major end moraines that make up the Des Moines Lobe. Across the Des Moines Lobe, you can see actually, it kind of sticks out, the Des Moines River. It's this kind of nice deep valley, and you can see where it continues up near Algona. The West Fork splits here. And these are the four study locations. Howlett near Esterville, like 2 miles from the Minnesota border. Wilden near Irvington, just south of Algona. Jenkins, just west of Boone. And then Avon Lake, which is near Carlisle and south and east of Des Moines. Across this transect from Howlett to Avon Lake is approximately 200 kilometers, just for your reference. Why did we think to choose these sites and so spread out along the river? That's because we want to, in this project, check for the influence of a climate gradient. Across the state of Iowa, climate changes a little bit. It's not uniform everywhere where you're at in Iowa, as you might expect. Mean annual temperature in the north is cooler, because you're at a higher latitude, than it is in the south. So mean annual temperature as you go south increases, the air temperature, and then mean annual precipitation actually also increases from the northwest, which is a little bit drier, to the southeast, which is more moist. Now, how does that change? Mean annual precipitation up near Howlett, so the northwesternmost location, approximately 780 millimeters in a year of average precipitation, and the southeasternmost location, 915 millimeters. Also, the temperature changes a little bit, mean annual temperature, 8.9 up in the north and 11 to the south. This is a map illustrating the same thing, precipitation across Iowa. Now it's in different units, it's in inches, but it's more just to display the nice concept, how you can see precipitation gradually increasing from northwest to southeast along this trend. And it's convenient that the Des Moines River kind of moves in that northwesterly to southeasterly direction. So that's why for the spacing. So we've discussed climate, and we've approaching this project from a climosequence point of view. That's based on Hans Jenny's 5 soil forming factors. Now, I just explained how climate changes, climate progresses across the state from the northwest southeast in mean annual precipitation and mean annual temperature. The 4 other soil forming factors, if you're doing a climosequence, must be held constant. So those would be parent material being another one, time, topography, and then biota. Parent material being outwash, time being approximately 11,000 years, The topography is very low relief terraces, and then predominantly prairie vegetation. We discussed climate. This is kind of discussing that parent material, that outwash. Specifically, this outwash is the Noah Creek Formation. It belongs to the Noah Creek Formation. Across the state, where this is deposited, it can be from 3 to 15 meters of coarse sand and gravel. Very little silt and clay. Like I mentioned before, outwash is typically low in that, unless you're a long ways from the source. In valley positions, it's often the oldest surface, the oldest terrace. Across the state of Iowa, it was deposited from about 14,000 to 11,000 years before present. However, it's more narrowly constrained in deposition because of the birth of the Des Moines River, or in association to the Des Moines River. Bettis and Hoyer pinned that date of deposition where the river was first cut to where then the outwash was aggrading between 12,300 to 11,000 years BP. This is kind of demonstrating the stratigraphy and the terraces, and of course this is a cross section here. This is an idealized cross section I made up of the Des Moines River Valley. You can see you have your Wisconsin and Till, so the Des Moines low aged drift, and you have the pre-Illinois and Till that is underlying it. You have your Till uplands, and these are your terraces. Now HT, high terrace, intermediate terrace, low terrace, and then modern day floodplain, and of course the Des Moines River. The high terraces, the oldest terraces that we see, are going to be Noah Creek Formation, the outwash, and then once the ice age ended and the glaciers retreated farther north, the river had less of a load and was able to downcut, and you started forming these later terraces that are DeForest Formation alluvium. You can see this is also a useful demonstration to show the challenges with finding a suitable research location, because rivers like the Des Moines River are dynamic, they meander. They destroy terraces gradually over time. So they create them and then they destroy them. And so you can see here in this example, the intermediate terrace has been destroyed as that river meandered, forming like the low terrace. And over time, if it keeps meandering, you lose all of this. It's also complicated by the fact that you could have an alluvial fan deposit or colluvium coming down and depositing on top of that high terrace that you want to target. So an ideal site would be studying the soil right here. What makes up this outwash? This is some quick just lithology, what's in it. This is based on some pebbles, pebble fraction that was identified in a study by the U.S. Geological Survey. These are the major rock types or mineral types that make up these pebbles. You can see limestone is the most dominant member here in these findings, 33%. You can see some of the other common ones. I want you to remember limestone, 33%. That's 1/3. That's a lot. So you can imagine if that's making 1/3 of the mass of that starting outwash before you have any soil forming, any addition of rain, etc. What if we removed that? What if we leached all that carbonates out? You can imagine the pedological changes that would happen. For example, bulk density you'd expect would drop. You'd open up those pores. You'd also expect perhaps clay to increase because there's impurities in the limestone, often clay-sized impurities. You dissolve these coarse limey frags, these limey pebbles and sands, and you might release these impurities. And okay, moving on to another soil forming factor, topography or relief. Typically very low relief. This is one of the study locations, Wilden. I took cores from this field here, and it is gently sloping to the southeast. This is actually the Till upland. This is the Des Moines River here. This is LiDAR imagery. Sorry I didn't say that first. And it drops in elevation gradually from about 3 meters from here to here, about across half a kilometer distance. Something I want to mention before I forget, when I use the term location in my presentation today, a location refers to Howlett or Wilden, the actual field. And if you hear me say site, I'm referring to an actual coring site where soil cores were taken. So there'd be several sites at each location. The last soil forming factor I'd like to mention is biota. which has been dominantly prairie grasses over the history of the soils. There would have been, once the glaciers left and you stopped depositing outwash, there would have been a plant succession that would have happened. You would have first had your colonizing species such as lichens, and you have some mosses come in, some sedges and grasses, and then eventually coniferous forests, and then eventually deciduous. But for about the last 3,000 years, it's been controlled by prairie dominantly, and that's why we observe mollisols typically, which is interpreted as forming in prairie. Moving on to the methods section. So I did say there was 4 study locations, research locations. Cores were only able to be used from 3 of them. That's because the Jenkins site, the one near Boone, however, while it met these 3 primary criteria, appropriate age, the right landform on these superficial geology maps provided by the state of Iowa, it had outwash soils mapped, and it even looked good when we inspected it. For example, I would say there was lots of big pieces of gravel just on the surface, pebbles and even cobbles up to the size of a person's skull. It looked very outwashy. However, the cores, when these profiles were described, it's almost all fine to medium sand throughout the profile. So it could be that that was a lake deposit. So it wasn't outwash, so we had to throw those cores out. All these collected cores were taken in pairs, so actually duplicate cores at each coring site. One was for study, one was to be held on reserve. And of course, being a pedology study, profile descriptions were made on all of them. Some of the analyses that were done, we measured bulk density, did a particle size analysis, measured total carbonates in the form of calcite and dolomite, measured pH, and as well as soil organic carbon, converted from loss on ignition to measure soil organic matter. We also did a mineralogical analysis on thin sections that were prepared from actually those duplicate cores that I mentioned that are held in reserve. We selected a chunk of soil, so to speak, from the master horizons of each profile. From the midpoint of the A horizon, the midpoint of the B horizon, the midpoint of the C horizon, sent them off and had thin sections made. This is one example. I think this is from Wilden. This would be from an A horizon. This colored portion is where, using the program's cell sense dimension, we created a region of interest. And these colors are actually programmed or represent the different mineral, so to speak, groupings. Those groupings were colorless to light tan minerals. Then clay, like the clay, organic matter, the really fine stuff you have to kind of lump together because it can't tell what that is. The really dark stuff was a grouping. The blue is actually a resin dye. That's the pore space. And then there was these brown concretions that were given their own group that were kind of anomalous, and so, but they were minor constituents. That was the 4th grouping. If you're, not to dwell on this too much, but this white stuff around the edges is just this extra sand they use to prepare the slides that they grind. You can tell clearly the soil that is being examined from that extra stuff. Point counts were made on only 3 slides because basically we ran out of time. And that data is not presented here. The last measurement, so to speak, kind of a measurement, is we calculated or estimated the mass of carbonates that would be removed across these different sites, these different locations from northwest to southeast, using the mean depth to carbonates or mean depth to effervescence. Transitioning to results. It's kind of a fun picture, huh? It's from a BC, or I think it's a Cambic, so a BW horizon at Wilden. I'm just going to flash this chart briefly. This is more for something we can come back to if you have specific questions about the trends across the 3 research locations. The 3 that were remaining, Howlett, Wilden, and Avon Lake. This is a summary of what their A horizons and B horizons, C horizons, the master horizons typically looked like. Just a couple things I'll note is that clay was pretty much consistent across the A horizons and the B horizons and the C horizons across from northwest to southeast. There's lots of coarse fragments in Howlett and Wilden, and there's a lot less in Avon Lake. So 36% coarse fragments, so things larger than 2 millimeters, versus 6% here. One asterisk is that during probing, we were not able to get deep enough with the probe to collect true sea horizons because we kept hitting too much gravel. You can only go so deep and hit so much gravel and you just can't get to it. So that data is approximated utilizing BC horizon information to give an idea of what should be there. Some early results that were very clear, not real important to this study, but soil survey accuracy. So in this study we relied upon soil surveys telling us what we might find if we venture out on the landscape. When we actually went to collect the soils, we found that only 7 of the soil sampled actually belonged to to the soil series that would be the dominant one of that soil consociation. 7 out of the 25 are what they said should be there. 10 were belonging to either a geographically associated soil, or series, excuse me, or otherwise competing series. So 10 have a competing series, and then 8 were observed to be completely outright wrong, belonging to either a different suborder or order altogether. So, kind of fun. And other people found that in their studies as well. That, yeah, they're useful. Moving on to particle size information. This is a graph. I'll talk. All my graphs are going to look pretty similar. This is mean particle size, increasing this way in micrometers, depth below the surface. So each point actually represents a sampled horizon from cores across these sites. We have the blue squares are from Howlett, the northwesternmost. The orange circles belong to Wilden, the middle location. Relatively middle, it's farther north, but not the dead middle. And then Avon Lake are these gray triangles. You also have the trend lines plotted as well. So virtually all these soils had finer textures overlying coarser textures, which is observed. So we found that was confirmed. Often loamy, often loams or clay loams over sandy loams, or gravelly sandy loams. There wasn't very good t-test values, so it's hard to say any trend across from northwest to southeast for the geometric or the mean particle size data. Clay amounts were found to be inversely related to the geometric mean. This is from the same core, Howlett 8A, depth below surface, increasing mean particle size, increasing clay percent. You can see the inverse relationship. So it makes sense. The more clay you have, that's a smaller particle. So your average particle size in that soil should be smaller if that's increasing. Clay amounts typically decrease with depth, actually very nicely, very predictably, with the exception of the very few, 3 profiles that contained argillic horizons. There's actually 1 at each of the 3 locations I mentioned. 1 at Howlett had an argillic horizon, it was an RGU doll, and then 1 at Wilden, an RGU doll, and then 1 at Avon Lake was a RGU doll. So a model soil with an argillic horizon. No clear trend though relating clay to pedogenesis from northwest to southeast was observed because it didn't really change, as I pointed out earlier. Bulk density for virtually all the sampled sola increased with depth, which is pretty typical, especially soils in Iowa, but there's no trend across the 3 locations. This is bulk density increasing and depth. Same little guys represent the same information again. Something we did in this project is looked up what would the bulk density be at time 0, so when we had outwash, and then tried to figure out if we leached all that carbonates. Remember we talked about 33% carbonates, and on average in the sea horizons that I examined, so the relatively unaltered paramaterial, the average carbonate value was about 25%. So conservatively we assumed 25% carbonates, and then we removed that either through reaction or leaching dissolution out of that upper portion of the soil, what would that bulk density be? How would that change? And if you remove 1/4 of the mass, you end up with approximately 1.27 grams per cubic centimeter. Now 1/4 of 1.6 is 1.2, but we assume there's some clay and magnesium from the minerals being left behind in the soil. So that's the estimated resultant bulk density after leaching those carbonates. And ironically enough, the average bulk density in those surface horizons was 1.3 across the sites. So it fits well in there, and you can imagine there'd be additions of organic matter that increases bulk density, and maybe some fluffing up from some bioturbating animals and stuff. pH, moving on to pH. pH increasing, depth below surface. Not going to dwell on this much because it wasn't plausible to claim any trend in pH because it was just all over the board. And basically human impact, land management decisions overshadow any natural influences is what we're saying. Really acidic soils were observed at one site, dangerous to production level acidic soils like some 4s. That's not good for plant growth, as many of you in this room know. Mineralogy. So similar graph again. This is what was conducted in those thin sections. Remember the colorful thin section that I showed. This is the abundance of these colorless tan-colored minerals. This would be, and this was a way of, this was just basically a method of doing this quick, to get a quick glance at what the mineralogy is and how it changes with depth. These colorless to light tan minerals would include primarily quartz and feldspar, but also the carbonates when present. So this is the percent of that cross-sectional area. And what we see here is actually reasonable correlations like 0.35, that one's kind of weak, but 0.5 and 0.72. We can kind of see that there's a trend that at Avon Lake, which is the gray, so that's significantly farther southeast. This might show evidence of deeper soil development, so the influence of that climate gradient, because we have fewer colorless minerals, so quartz and feldspar occupying less of the that stuff is occupying less of the, I'm getting tongue-tied, sorry guys, the cross-sectional area. That is to say there's more clay and organic matter stuff. And this will kind of make sense when I show you the soil organic carbon here. More soil organic carbon at depth than Avon Lake, southeasternmost location. This one's kind of fun. Strong correlations between depth and soil organic carbon. And in the north, so the blue line is the northernmost, we have the most soil organic carbon, and it decreases in these surface horizons. This could likely be that you have cooler temperatures and less precipitation, so your decomposition rate would be lower, higher at the south, warmer temperatures, a little more rain. And then it flips. Lower in the profile, it's the opposite. So you have, so more soil organic carbon at Avon Lake than there is at Wilden in the middle.